All right, let's talk about advanced manufacturing. You're probably aware that we know how to build GPU chips at nanometer precision. We even run factories that look like complete science fiction with robots inside it. And to be honest, I had always thought about it this way. It's simple, you design the process, you optimize it, you scale it. Except that's not really how it works. In fact, products fall on the distribution. Some of them are great, some of them are acceptable, and some of them get scrapped because they're not good enough. And in that process, we lose a lot of money. But we also harm the environment much more than we should. But is there not a better process? My name is Hugo Roche. I'm an early stage climate tech investor at Climate Club, and this is New Wave with Jared O'Leary, co founder and CEO of SirenOpt, a company trying to make advanced manufacturing actually observable in real time. Jared, welcome. Before we started this conversation, we were quickly chatting about the world of manufacturing and the efficiency of the factories that are running today. Tell me more about it. Are we efficient today at doing advanced manufacturing?
I think to answer that question, we'd have to define what we mean by efficient, right? Like certainly we have extremely advanced manufacturing processes, right? And certainly we have companies that are making massive profits, right, from that manufacturing, right? That being said, every sort of advanced manufacturing process in the world loses enormous amounts of money to scrap, or to taking time to build up their lines to reach some sort of profitable yield. And so I think overall, like the best way to answer that question is to say, like, yes, extremely advanced manufacturing exists all throughout the world today. Almost all the products we interact with every single day involve some extremely sophisticated process, but there's a lot of room for improvement in this process.
And obviously, with SirenOpt, you cover a lot of industries, but let's take battery manufacturing as an example. It's obviously critical for the energy transition. It's obviously quite advanced manufacturing process. When we think about battery manufacturing as an example, do you have any rate of defect or success rate? Like, what does that look like?
I think there's lots of information in the literature that claims certain scrap rates or certain yield rates, etc. But those are all sort of estimations, right? Like the true efficiencies of factories, the true defect rates, the true scrap rates, the true uh, uh, quantifications of the sort of state of these battery manufacturing plants are very, very, very proprietary and are very much sort of trade secrets, right? And even in sort of defining yield, like even asking the question, like, what is the yield of a certain battery manufacturing process, right? In itself is sort of imprecise, right? Because, if I'm a company and I'm claiming, okay, I have some 98% yield, whatever it is, right? What's actually happening is out of the sort of accepted products, these companies are binning those accepted products, right, into like 8 or 10 or sometimes more classes and selling all of those sort of accepted products for vastly different prices and in many cases vastly different applications, right? So what's like very, very common for battery manufacturing, for example, is that, let's say I'm a battery manufacturer and I manufacture 100 batteries that have all passed quote unquote my spec, right? Well, I'll only sell a small percentage of those to like high performing EVs, right? I'll sell another percentage to lower performing EVs, and I'll sell like another percentage still to like things like consumer electronics, right? So it really is sort of difficult to truly answer that question. Right?
And it's interesting because for me, I've always thought about manufacturing as a deterministic environment. In other words, you create something, it works or it doesn't. You're telling me right now that actually it's quite the opposite, that you have a certain range of like, it works actually. How do you describe that?
Yeah, I would say the easiest way to imagine sort of advanced manufacturing or in particular advanced materials manufacturing, right, is that the quality of manufactured products will always exist on some sort of distribution, right? With the vast majority of products being in the center of that distribution, having some sort of okay performance, and then some products on one end of the distribution, which are the highest performing products, which either drive end product performance or encourage premium pricing, and then products on the other end of the distribution, which a lot of times are so poorly manufactured that they need to be scrapped entirely.
And could we ever move away from kind of this probabilistic environment? Like, is it possible to actually say, I'm going to always hit a certain, specs basically for battery or any other good?
Yeah, so the existence of that distribution really is intrinsic to this type of manufacturing. I think the only way that you could have like truly deterministic manufacturing in like advanced materials context, is, I would say truly like with like zero variation, right? Is somehow if these manufacturing processes were to occur at like absolute zero, and there's no like random movement of particles or something like that. But those distributions will always exist, right? But I do think we absolutely could live in a world where those distributions are so thin, right? That like the end user of these products really does not notice a difference, right? Between products on manufactured products on either end of that distribution. And like, that really to me is like, the ultimate goal of these, autonomous factories or a lot of this, physical AI or industry 4.0, et cetera, right? Like, if you're driving an EV, do you really notice if the range on that EV is 1,000 miles or 1,001 miles? Right? You don't, right?
In
Yeah.
other words, what you're saying is that we got to a point where we're making the products. It is at relatively good quantity of like great output versus good output versus bad outputs. But what you're saying is that we can actually move that distribution more towards great. Is that how I
Yeah,
should think about it?
exactly. Exactly, right? And another thing too, and this is something that I think is really understated, right? Is we are talking about, hey, we're talking about this kind of purely in terms of performance, right? And we can move a distribution kind of more to the right and have like less variation, etc., right? But one thing that I think is understated is that manufacturers know that there's a lot of like uncontrollable variability in their processes, right? So one way that they account for that is actually operating their manufacturing processes in a very hyper conservative way, right? So I can give two good examples of that, and they're both in batteries, right? So that the battery electrodes, if you're familiar with the term or not, but they're basically the kind of core component of batteries, right? It's kind of where all of the active reactions occurs, where all so the transport occurs, et cetera, right? Well, like battery electrodes today are made 30 to 40% thicker than their like optimal thickness, right? And like the reason for that is manufacturers know that there's going to be some unavoidable defects, and sort of like the effects of those defects are sort of mitigated at larger thicknesses, right? Or in a lot of places as well, we talk about battery manufacturing going at 100 meters a minute or whatever it is. Well, those machines that kind of do these manufacturing processes can move much faster, right? But they're just operated more slowly, right? To to sort of help mitigate or like account for this variability, right? So there like really is a big aspect, I think with all this. It's not just okay, let's have less variable products, but like if we didn't have to operate our processes so conservatively, we could also just have much higher performing products.
What's interesting is that we are talking about the performance of the product, but from a financial perspective for the company producing these batteries, it is also a massive impact. I think I had a number in mind, you'll correct me if I'm wrong, but I had 275 million lost annually per plant for a 50 gigawatt plant output of batteries. Um, that is just a massive amount of money because of just like scrap batteries or like batteries that are going to waste or that are not at a good enough quality. So I think that's also core to the problem is not only the quality of the output, but it's also like how much money you lose as factory.
Yeah, totally. But a point I'm trying to make is that like those two things aren't really separable, right? Like
Mhm.
like like if I can make my electrodes thinner, I would also save money, right? There's other things too where like it's been very commonly reported that like battery manufacturers will overbuild their battery packs to like account for variability, right? So though it's been reported that battery manufacturers will put up to 10% more cells in their packs than are necessarily required, right? To mitigate some of this variability. And what's very interesting to me is like battery manufacturers can do that, and to me, that extra 10% should be counted as a yield loss, right? Because that is like using 10% more material than you should. But when these guys report their yields, they don't say that, right? So it gets this really interesting thing where I think yield and performance are generally treated separately, right? People look at us, for example, and say, oh, you are just reducing scrap, etc. But these things are like so intertwined that there's no real clear way to sort of separate them.
All right, well, let's talk about SirenOpt and the path to high yield manufacturing. So, what the premise of what you're doing today is to say that if we were to be able to measure better and at a more precise point of time, we could maybe improve on all of these metrics. Tell me how that thesis came together.
Yeah, yeah. So one in let's just take battery manufacturing as an example, right? Uh, I think I mentioned these like various causes of variability, et cetera, right? But right now, especially in battery manufacturing, right? These manufacturers do have a lot of information, right? They have a lot of information about the process, but the information that they have is basically put into two categories, right? So they have a lot of information about like the inputs to various machines. So they have a lot of like information about like what is my machine doing and like how is it running, right? And then they have a lot of information about what comes out of the machine, right? About what's at the end of the line. But there really are massive, massive blind spots in the middle there, right? And basically, the sort of defect formation and property evolution of these advanced materials that do ultimately govern the yield, performance, and safety of the end product are really missing, right? These manufacturers like really cannot see that, right? So our immediate value add is just providing a wealth of like very critical and otherwise unobtainable information, right? And I think a fair follow-up to that is, okay, well, if I have this information, well, how can I improve these processes, right? Well, you could basically the dream here, right, is that manufacturers have this information. They say, oh no, my process is variable in X, Y, or Z ways, and they have this extra information so they can react to that, right? And sometimes that reaction is as simple as, oh, this material is bad, let me cut it off the line, right? And let me cut it off the line earlier before I've put it through 100 more processing steps, right? In the most advanced form of this, it's, oh, I see my material is starting to vary, right? Now let's have software automatically tweak some manufacturing process parameter to literally mitigate that variability in real time to ensure that this does not become a defect and that this can be, X, Y, or Z, high performing material.
And what's very interesting, what you're saying is that if we were to kind of say, okay, my material is not good enough, let's stop the line now instead of having a bunch of batteries coming out that are basically not usable, um, that also means that you basically need to have the data in real time.
That's exactly
You
right.
have
That's exactly
so
right.
how do we do that?
Yeah, yeah. I mean, so in the case of SirenOpt, right? We have created a novel real time measurement instrument that can be integrated directly inside of high volume manufacturing lines and can measure the critical properties of these materials in real time and inside the line, right? So we are really providing information back to manufacturers on millisecond timescales, right? uh Now that's important thing I want to clarify, right, is that you know I think I've sort of made it seem like, look, there are zero inline measurements or zero real-time measurements today, and that's certainly not true, right? There are people do get some information inside the manufacturing line, right? Now, the information they get is generally optical from cameras or maybe from, certain types of X-ray, etc. But that information is certainly incomplete, right? So we will basically exist in kind of the same spots in the line, etc., as these existing tools, right? And we will add a wealth of information, and that information will go into the existing workflows, that are there that sort of use this type of information.
Yeah, because I think what's happening so far is, as you said, you have very simple kind of camera-based analysis. You also have sampling happening, people just taking out a sample
100%.
from the factory.
100%.
But what you're saying is that you can basically, through a technology that you've developed, you can basically do it throughout the line with something that is not sampling, that doesn't require kind of taking out something from the
Exactly.
line and putting it back later. So, I mean, what's the technology that allows that, which is not a camera?
Yeah. Uh, our sensors enabled by our tools enabled by what are called cold atmospheric plasmas. And if you're not familiar with that, maybe you are familiar with plasmas in general, which are basically weakly charged gases. Plasmas, if you care, are considered the fourth state of matter, and they are technically the most common state of matter in the universe. But basically, like stars are made of plasma, sun is made of plasma, etc. We basically create a cold atmospheric pressure version of that, right? So imagine, atmospheric pressure, weakly charged gas that sits at about 40 degrees Celsius. Um, these plasmas are unique because when they come into contact with incident materials, they induce these synergistic plasma material interactions. So you have this unique scenario where the material, interacts with the plasma or reacts to the plasma, and the plasma responds to the material, right? And our core thesis is that those plasma material interactions are extremely informative, and that if we can record those interactions sufficiently well, we should be able to translate those interactions into multiple critical material properties, right? So overall, our core thesis is, hey, if we expose material samples to cold plasma, we create a ton of information, right? We can then use off-the-shelf detectors to record all that information, and then use physics-based software and models, etc., to translate that information into actionable data and insights for the manufacturer.
Well, seems like a great thesis, but does it kind of break the material? Or like what happens to the material really?
Yeah. That's a great question. So, this is a non-destructive method, and we have, I think, tested that and validated that, extensively over the last, 3.5 years, of the product, right? Really, what happens to the material is the material is exposed to some ions, right? Some aspects of that material do get excited, right? But no aspect of the material sort of changes its performance, or at least in some measurable way, right?
You're also the person measuring it. So
Well, every time we sort of interact with customers, the like first thing that we do is we'll have them send us some samples. We will measure those samples. We will send those samples back to them to do their own measurements that sort of verify the non-destructiveness of this. And this may seem sort of counterintuitive here, but you can very easily verify the quote unquote destructiveness of our method with other types of measurement techniques that cannot exist inside of manufacturing lines, and that actually, believe it or not, destroy the sample. So that might seem counterintuitive. So just to be clear here, every single thing that we measure today inside the manufacturing line in real time can be measured off the manufacturing line with very fancy instruments that every manufacturer today has in their possession, right? Just those instruments often destroy the sample, and obviously cannot be integrated inside of the line.
okay, so the critical thing that I hear from you is it has to be a real time scenario and it has to be non destructive. Those are the two things to solve for high yield kind of advanced manufacturing. Is that correct?
Yeah, I mean, I would say like that's the first step, right? So, I think a good way to phrase this is the following, right? Is, I think the dream of advanced manufacturing, right, is really what people use the term industry 4.0 or industry 5.0, et cetera, right? Really what they're referring to are these, autonomous, self-optimizing factories that, correct defects before they ever occur and don't need any people, et cetera, right? And I think a lot of people really think that the key to achieving this, these autonomous factories is all in advanced software, right? And that's true to a degree in the sense that, right, like, you obviously need advanced software to like do these types of optimization and like run these plants. But there's a step before that where you need the data to feed that software, right? So, from our perspective, like really the path to autonomous factories is really paved with creating collecting more data in real time inside of these advanced manufacturing lines.
Okay, because the future of that could be that basically SirenOpt collects the data and then the software comes on top with maybe a robot or whatever, and then changes the
It,
factory line.
and that is exactly the dream of this company, right? It is, yeah, it is really to provide the sensing hardware that like collects all this critical data, and to provide the decision making software that one day would ultimately adjust manufacturing operating parameters in real time to mitigate manufacturing variability in real time.
That's very interesting. When I think about SirenOpt from an investment perspective, one of the first thing that comes to mind is I don't think factories are known to be quite early adopters of new technology, specifically on their manufacturing lines. What has to happen for this to become kind of the new market standard for measurement? Like, how do you make it so that they accept your technology in their lines?
Yeah, so certainly there are evaluation periods, right? But I would push back on the comment that manufacturers don't adopt new technologies, right? I mean these companies are constantly evaluating and looking for new tools to give them a proprietary edge in their process, right? Because I think something people don't necessarily understand, right, is all of these advanced manufacturing lines have, thousands and thousands of tools from all sorts of different vendors that do all sorts of different things, right? And the placement and use of those tools, right, is absolutely considered like a proprietary trade secret for each of these companies, right? And and I know we've been talking about batteries for forever, right? But I think a good example is like someone like TSMC and semiconductors, right? TSMC doesn't make any of their own tools, right? They buy advanced tools from the Applied Materials and the Lam Researches and the ASMLs of the world, right? And I think a fair question is, okay, well, why, if TSMC is buying tools from ASML and Applied and Lam, why don't ASML, Applied, and Lam make semiconductors as well as TSMC, right? And the fact is that there's an extreme amount of nuance in figuring out how to use the best combination of tools in the best way, right? So there really is this sort of constant evaluation period. Now, that evaluation period can be lengthy, right? But there is infrastructure already for that, right? And at least in our case, right? I've kind of discussed at length, right? There's sort of inline real-time versions of our tool, right? But we also have a version of our tool that can sit next to a manufacturing line, right? Where there's much lower risk for adoption, right? And that will be, and is the first type of tool that manufacturers purchase, right? And that, provides us some revenue early on, but it also allows these manufacturers to be, you know, familiar with the technology and trust it, right? And then we go from a benchtop scenario, right? And then we can go in sort of one of two scenarios, right? We could go to a pilot line scenario and be evaluated for another 6 months, right? But another beauty of, I think our platform is that it actually is really, really compact. And that makes a big difference, right? Because if you have a compact tool that is non-destructive, that is core value add is measuring a bunch of things, properties that aren't being measured all today, you can put that on your line and monitor the performance, right? You don't have to use that information for anything, right? but you really do have the opportunity to stick this in the line and say, okay, like let's just monitor the monitor how this tool is performing over the last 3, 6, etc. months, and see if we can integrate it into our workflows.
Yeah, worst case scenario basically is to say that you have data that you're not going to use. That's
Exactly, right?
okay. That's very interesting. Um, I mean, it seems like it makes so much sense to have this tool. Why has nobody else built it before?
Yep. Yeah. So this is this is kind of an interesting background here, right? So, we are the first people to use cold plasma for, measurement, you know, materials measurement ever, right? Um, and just to give background on how this company started, so I co-founded this company with my former PhD advisor based on research I'd done during my PhD over at UC Berkeley, right? And um, our research, we were actually looking at and using cold plasma for an entirely different application. Uh, and really, believe it or not, what we were trying to do is we were trying to develop like really like advanced software strategies to control cold plasma, actually for a biomedical treatment application. So basically, and this is actually very popular in Europe now, believe it or not. A lot of European doctors are really interested in using cold plasmas for wound healing and for skin tumor treatment. And the problem we are trying to solve is if I have some handheld plasma jet and I'm treating someone's wound, etc., right? Well, what happens if I move my hand or the environment's variable, etc.? The plasma is going to change, right? So we developed some advanced, really embedded control strategies that basically allowed the plasma to remain consistent in the face of, other, environmental exogenous disturbances, right? So and then kind of over the course of that research, we knew there was a lot of information on the resulting plasma material interactions, and we thought, hey, maybe this could be a sensor, right? But I give you that background to say that really the core enabling technology here is in how we control cold plasmas. And we were the first people ever in any academic or industry context to explicitly try to develop, embedded control strategies for cold plasmas, right? So although I rambled for a bit there, the short answer to your question is we are the only people that can use cold plasmas for measurement because we're the only people that can control cold plasmas. And we were the first people to even think of really truly, we were the first people to even think of trying to create embedded feedback control strategies for cold plasmas.
I mean, maybe we'll end on that question for today, but when we think about batteries or even solar panels and other critical technologies for the energy transition, a lot of people think about kind of the next breakthrough of like chemistry to make it cheaper, to make it better, more performant, right? Um, Maybe my key takeaway from today, and let's see if you agree with me, is that if we're able to produce better, have a more consistent quality of output, less scrap, then maybe actually we don't need that breakthrough at all, or maybe we can wait a bit more. Is that a good understanding of the situation?
So it depends how you define need, right? And what I would say for us is I actually view a really big value at a really big dream for us is actually enabling these next generation technologies. So let me give you an example, right? A lot of people are making batteries for EVs. No one is making batteries for 747 jets at scale, right? And the reason for that is the types of chemistries that would enable these 747 jets, we basically can't manufacture, right? So I actually view it in maybe not the opposite, but in a different way, where this type of technology can actually allow these more advanced breakthrough chemistries to be able to be manufactured in a scalable and economical way, right? So for example, let's take solid state batteries, right? I think everyone agrees that solid state batteries could provide enormous societal benefits, right? But no one has been able to manufacture solid state batteries in an economical way, right? And we view technologies like ours as a key enabler for like putting these advanced chemistries in the market, right? And it even gets to, I think a big reason why I started this company, right, is over Berkeley my PhD, right? You'd see, almost every week some academic group would write some new paper that was like, hey, with advanced chemistry X, we've now made a battery that's 90% better than everything else that exists, right? But if you can't manufacture that chemistry, right, it doesn't matter.
Mm.
Right? So we really do, overall, I would say, we really do view ourselves as a core enabler of the next generation of advanced materials, sir.
Yeah, I love that because it's about optimizing what's already existing today and also being able to develop the next breakthrough.
Exactly. Exactly.
That's a great way to end this podcast in terms of the future of manufacturing. Look, Jared, if people want to reach out to you after this episode, what's the best way to find you online?
Yeah, so you'd send me an email, Jared, JARED.OLEARY@SirenOpt.com. That's SIRENOPT. Could also, if you're interested in working with us, you could just send an email to info@SirenOpt.com. We actually do have a whopping 31 full-time employees now, so we can we can take various types of inbound interest, etc. And the last thing I'll say is, if you're ever interested in trying out this technology, etc., the beauty about having a company where its core product is a measurement instrument is it's very easy to test out, right? It's very easy to send us samples and have us run them, or sort of even show up. We also invite people to our campus all the time to bring their own samples and measure them live in front of us, things of that sort.
I love that. Super. Well, listeners, if you like this episode and if you like the show, don't forget to like, comment, and subscribe if you're on YouTube, or to give us a follow and a 5-star review on Apple Podcasts and Spotify so that we can invite more and more amazing guests. Thank you so much, Jared.
Yeah. Thank you for your time, Hugo, and thanks for asking such great questions. And yeah, I really appreciate being able to be a part of this.